Let's go to example 6, our last example for this section. We have another function, x plus x squared. We're going to look at it over the interval from 0 to 1. We're going to find the formula obtained by dividing 0 to 1 into n equal subintervals. So instead of specifically saying 4 or 5 or 6, and then we're going to use the right-hand endpoint for each value. Take the limit as n goes to infinity to calculate the area under the curve over 0 to 1. Okay, so what I did over here on the left was just first of all draw us a picture. It's basically just a gentle curve going from 0 to 1. Now it says what we want to do is divide this interval, which is usually of length 1, into n subintervals. So that means that our change in x is going to equal the difference, so 1 minus 0 divided by n, or each of the intervals is just going to be represented by 1 over n. So we can think of the intervals as being 0 to 1 over n, and then the other one from 1 over n to 2 over n, and then we have another one from 3 over n to 4 over n. So y'all can see the different intervals all the way up to n minus 1 over n times n, or up to n over n. Okay, so this will give us an intervals from 0 to 1, where each individually in between there is a distance from 0 to 1 is 1 over n, 1 to 2, each of these is 1 over n in length. And now specifically, since they said that we for sure want to be using the right-hand side, or the right-hand endpoint of everything, so when we go to our main formula to be able to find the summation, is remember it's going to be f of the right-hand value in there, which is going to be 1 over n, times the length, which is 1 over n, plus f of, and this next one, the upper hand one, would be 2 over n, times the length, which is still 1 over n. Okay, and then the next one, the next interval, the upper hand, will be 4 over n. Its length is still 1 over n. Okay, all the way up to f of n over n, where its length, though, is still 1 over n. Okay, so this will be the estimate of the summation. Okay, and just going back real quick, I have skipped one of those in there. 0 to 1, 1 to 2, that should be 2 to 3 right there. Just notice that real quick. I was like, oops, I skipped that. 2 to 3, but then the upper one obviously is 3. So as you can look at the tops of these, it's always times 1 over n, but look how it goes 1, 2, 3, next one would be 4, then 5. Well, we can use that and write a general summation rule for all of that we've been practicing in the very first part of this lesson. Okay, so in general, if we wanted to try to sum up what this line is saying right there, then it's going to be the summation from k equals 1 to n, f of k over n, because remember that's going to be 1 over n, then 2 over n, 3 over n, but we're always multiplying by just 1 over n, so that one's going to stay just the way it is. Okay, so we're only going to put the k in the top spot. Okay, and to keep working with this just a little bit, then it's going to be the summation from k equals 1 to n. Let's put our function value evaluated there. So our function value is x minus x squared. Well, this right here is my x, so it'll be k over n minus k squared over n squared, then times 1 over n. And it was actually sum, so let me go back and put a plus right there. Okay. Going on to the next step, we just kind of want to clean this up as best as we possibly can. So that's going to equal the summation from k equals 1 to n, distributing here, so it would be k over n squared plus k squared over n cubed. Okay. And if we use some of our rules for summations, we can break these up into 2 individual ones. So we can just isolate and try to get an answer for both of them. So it's going to be k equals 1 to n of just k over n squared, and then plus the summation of k equals 1 to n of k squared over n cubed. Alright, so let's keep going. In each of these cases, the n squared, that's just a number. So we can almost pull that out front of the summations. So it's going to be 1 over n squared times the summation from k equals 1 to n of just k, and then plus 1 over n cubed times the summation from k equals 1 to n of k squared. All right, and we've got special formulas for both the first and second part here. Okay, using our special formulas, we know that this is going to be 1 over n squared, and the summation from 1 to n of k, they tell us it's going to be n times n plus 1 over 2. And then the summation from k equals 1 to n of k squared, they tell us that's going to be n times n plus 1 times n plus 2 all over 6. All right. Okay, so from here on out, let's just kind of clean up a little bit of what's going on over here. If we cancel out one of those n's with that n right there, one of those n's with that n right there. See over here on the left, let me give us some more room. On the left, we have n plus 1 over 2n. And on the right, if I go ahead and multiply those out, we'll get n squared plus 3n plus 2 all over 6n squared. Okay, I'm thinking about just kind of each of these fractions is divisible by one term, so we can write it as like n over 2n, which is a half, plus 1 over 2n, plus, if I go n squared over 6n squared, I'll get 1/6. And then again, I'll get 1 over 2n. And then looks like 1 over 3n squared. Okay. 1/2 plus 1/6. We'll get 4 over 6. 1 over 2n plus 1 over 2n is just going to be 1 over n. And then that'll leave us with just a 1 over 3n squared. Okay, if I combine these two last terms, because they both have at least an n in the denominator, then we'll get 4/6, which is 2/3, plus, it looks like if I put a times of 3n right there and a times of 3n right there, we'll get 3n plus 1 over 3n squared. Okay, and so if I look at this as when n goes to infinity, that means anytime because this denominator down here has a power larger than the power up in the numerator, this whole thing right here is technically going to go to 0. So then the answer is just going to be 2/3.